Hi everyone, I'm Anirban. I'm a postdoc at Slack. Before I start, I want to thank the organizers of this workshop for giving me this opportunity to present my talk here. I'm going to talk about neutrino self-interaction as a solution to the Hubble tension. The meaning of this question mark in the title will be clear as I go along. This is based on this paper that I wrote with my friend Shobhajit Ghosh from Notre Dame University. Here is an outline of my talk. First, I'll tell you about the cosmology of self-interacting neutrino and also about the previous work that has been done in the context of flavor universal self-interacting neutrino, or SINU in short, how it tries to address the so-called Hubble tension. Then I'll come to the laboratory constraints on this, on SINU. And finally, I'll tell you about our work, how that laboratory constraints motivates us to consider flavor-specific self-interacting neutrino and what's the result of that. In these three previous papers, a very phenomenological model of neutrino self-interaction has been assumed. New phi type coupling between the neutrinos and a mediator phi. This mediator could be anything, could be a scalar or vector, doesn't really matter for cosmology. But this coupling matrix Gij has been always assumed to be a diagonal and with equal entries. So it's a flavor universal case with all the neutrino flavors having the same interaction strengths. Below the mass scale of this mediator, you can write down an effective 4-Fermi interaction between the neutrinos with an effective coupling GF defined as G square over M phi square, where M phi is the mass of the mediator. This plot here shows the time evolution of the neutrino interaction rate divided by the Hubble expansion rate of the universe. So this dot-dashed orange curve here is the electric interaction that neutrinos have in the standard model. So you see that this interaction decouples very early between the ratio of 10 to the 10 and 10 to the 9. However, in this plot, we'll be interested in a much stronger coupling. In fact, our coupling strength is about billion times stronger than the Fermi interaction. And we are showing here two lines, one for strongly interacting or SI and one for moderately interacting or MI. These two modes will become clear in a minute. But you should note in this plot is that for this SI mode, the interaction strength decouples just before the matter radiation equality. Now, to show the impacts of this self-interacting neutrino on the CMB power spectrum, I have borrowed these two plots from one of these earlier three papers. These are the residuals of the CMB power spectrum in the SINU relative to the lambda CDM model. You should look at this red solid curve here, which has two things. First, it has enhancement compared to the lambda CDM. And that's happening because in SINU, the neutrinos are not free streaming, and this lack of free streaming neutrinos enhances the gravitational potentials in the early universe. And that enhancement to the potentials transfer into the photon perturbations, and that finally affects the CMB power spectrum. That gives the enhancement. The second thing is the phase shift, which basically shows up as these wiggles in the residuals. The phase shift, the reason behind this phase shift will become clear in a later slide. And the similar is true for the polarization power spectrum as well. Here is a short result of this previous paper. This is the posterior of this new coupling strength GF. There are two modes. One is the strongly interacting mode, which I alluded to earlier. And there is another moderately interacting mode, which goes towards smaller value. And this is basically the lambda CDM limit. So this kind of posterior raises two questions. One is why there is a separate SI mode, and why it's discontinuous from the MI mode, why these intermediate values are disfavored by the data. Now, to understand or to answer these questions, we are plotting we're again going back to the residuals of the same power spectrum. So the zero line here is the lambda CDM limit. And to that spectrum, we are adding the SI mode values for the other cosmological parameters. So if you look at this red solid curve, we have added only the GF value of J effective. So clearly this is a very poor fit. It is way up here and it has lots of wiggles. But now if you keep including all these other parameters, H0, AS, NS, and tau, you are again going back to a very good fit, and the spectrum agrees very well with the data, and that's why you get a relatively that's why you get this new strongly interacting mode for larger value of GF. Similar for other spectra as well. And now why there is a gap between these two modes? So if you pick a value of GF from this value between these two modes, not all of the CME spectrum is affected. You change only a part of the spectrum, because not all the modes were inside the Hubble horizon when the coupling was when the interaction was decoupling. But all these other cosmological parameters, they change the whole spectrum. They are, in a sense, they are global parameters. So for these intermediate values of GF, you cannot play this degeneracy game and you cannot get a good fit. So that's why the data disfavors those values. Now, I'll very briefly will tell you about how you get a larger value of Hubble in SI scenario. So in self-interacting neutrino model, neutrinos, so in lambda CDM, neutrinos are free streaming, and that creates a phase shift in the same power spectrum. This phase shift phi nu is directly proportional to this quantity called R nu, and R nu is nothing but the free streaming fraction of the total radiation in the universe. So in lambda CDM, it's all of the neutrinos. In SI nu, it's less than that. So in SI nu, the value of R nu or phi nu is smaller than that in lambda CDM. Now, you can write down a relation between the positions of these peaks in the CMB power spectrum and this phase shift. If you decrease phase shift, as happens in SI nu, you increase L, which means you are shifting the whole spectrum towards right. Now you have data, so you cannot just change the spectrum. You have to cancel that effect. You can do that by changing this dA, which is the angular distance to the last scattering surface, and RS, which is the sound horizon during recombination. The only way to do this is by increasing Hubble, H0, and increasing omega lambda. And that's how you get a larger value of Hubble in self-interacting neutrinos. Now, coming to the laboratory constraints, in this nice paper, the authors have showed that in this simple model of neutrino self-interaction, you could look for constraints in various laboratory experiments and also from BBN. So here I'm showing only two plots from the paper. This is for universal coupling for all flavors, and this is only for coupling in the tau flavor. So you see that this green and the blue bands are completely excluded by BBN and laboratory constraints, but for when only tau neutrino is interacting, you still have some room left. That really motivates us to look for flavor-specific self-interacting neutrino. What happens in the cosmology? Here we have defined three cases: 3C plus 0F, where all three neutrino flavors have the same interaction strengths. That's basically the flavor universal. 2C plus 1F, where two neutrinos have interaction, and 1C plus 2F, where only one neutrino flavor has interaction. And we also only consider massless neutrinos. Here you can see the changes in the semi-pass spectrum in these flavor-specific cases. The red, if you go from the 3C, the red curve, to the 1C, the dashed green curve, you see that there is a continuous change, less and less amount of change in the semi-pass spectrum. And similarly for the polarization pass spectrum as well. And that's really easy to understand, because as you keep decreasing the number of self-interacting neutrino, you are going to the lambda CDM limit, and you gradually decrease the impact on the semi pass spectrum. So that's what's happening here. Here are the posteriors of a few important cosmological parameters, most important one being the posterior for G effective. For the flavor universal case, the SI mode is almost non-existent, you can see, compared to the MI mode. But in the flavor specific, for example, 2C and 1C, this mode is hugely enhanced. Why is this happening? This is happening because in the flavor specific case, you have less amount of interacting neutrinos. So the impact on the CMB pass spectrum is less, and you have more room to play with the degeneracy between GF and other cosmological parameters. So that enhances the significance of this SI mode. Another thing is the position of this SI mode, which is not really shifting. And that's because, as I told you earlier, for this particular value of G effective, the interaction was decoupling just prior to the matter radiation equality. And that is the sweet spot for CMB. And until that point only, you can use the degeneracy between G effective and other parameters. So that's why your CMB data is always choosing this particular value of G effective. Now, finally, coming to the about solving the Hubble tension. This is a posterior. These are the posteriors for G effective and H naught. We are plotting three contours: 1 sigma, 2 sigma, and 3 sigma. First thing to note here is that for flavor universal case, you get a relatively larger value of Hubble in the SI mode. So this red contour is sitting way up here between 69 and 70. But for 1C, the green contours are sitting somewhere down below. And this is because again, in case of 1C, the amount of self-interacting neutrino is less than the 3C. So you need a smaller change in Hubble relative to the lambda CDM value to cancel the effects on the CMB spectrum. So that's why you don't need to change Hubble that much. And as a result, you get a smaller value of Hubble. However, as in the previous case, the significance of this SI mode is increased dramatically. You can see for the red contour, we only have the 1 sigma contour, but for green lines, we all have all 3 contours. Finally, as in just to give an example, we got a value of Hubble 69.5 plus minus 0.6 for Planck temperature and polarization data, and including same lensing. Now this can be compared with local values of Hubble. One is from the TRGB measurement, which is at 69.6. This is completely in agreement with our number. But if you consider the latest reset all data, which includes uses CFIDs, they get a value of 73.2, and there is still a discrepancy between a discrepancy of 2.4, 2.5 sigma between these two numbers. So in this simple model, it's not possible to completely solve the Hubble tension. Finally, it brings me to the conclusion. We saw that the flavor universal G effective flavor universal values of G effective is incompatible with BBN and laboratory data, but flavor specific interaction might still be allowed. And we looked at that. We did not see any change in the value of the coupling strength for the SI mode in flavor specific scenario, but the significance of the SI mode is hugely enhanced, and that's because the impacts on the CME spectrum is less, with less number of interacting neutrinos, and there's more room to use the degeneracies between GF and other cosmological parameters. And in future, one could look at the case of massive neutrinos with off-diagonal couplings, and one has to see if anything changes in that more general, more realistic picture. With this, I'll stop here. Thank you. And if you have any questions, I'd be happy to answer them on Slack or during the workshop. Thank you so much.